right? June 17. Daily LeetCode problems. Day number 4. Do I sound cringe? Be honest.
A little bit.
Oh no! Why do I sound cringe, bro?
You sound like every YouTuber intro.
I know.
You're like, "What's up, guys? We're back with another."
Okay,
bit."
alright. Okay, I got it. True. Alright, I'm just gonna jump into it. Daily LeetCode problems, day number 4. Today we're starting with symmetric tree. So definition for a binary tree node class, tree node. So you have value, left and right, pretty standard data structure for a binary tree node. You have a constructor, which simplifies the process of inputting a value into a node, like 1, and we can set the left and right subtrees. So given the root of a binary tree, check whether it is a mirror of itself, i.e. symmetric around its center. So we can do this with a function, and this function has to do a particular symmetric mirroring to check the subtrees. So usually with the recursive function we'll pass in 1 parameter, but for this one we'll pass in 2. We'll pass in root and root dot right, and then we'll define this helper function. Yes, we'll define this helper function, and it's going to get the tree node values. It's going to be tree node or null, and right is going to be a tree node or null. Right, so since we have the left and right subtrees for a particular node, then the recursive function is going to check the symmetry between these 2 nodes. Before we can do that though, there's a few things we have to check for. If they're both null, then we want to return true, right? And we want to return true since they would both be terminating. So if we imagine an extra node here between 3 and 3 here, and let's just imagine that, 2 nodes here. We have a sub node, right, between 3 and 4, and we're both at those sub nodes. If they're both null, they'd be down here. Then that's good, right? That means they would be symmetric. Then we can do another check. Well, if one of them is null, we're checking if they're both null, right? So we have to check if one of them is null, right? Then we want to return false. The reason we can return false is we know they're both not null up here. If we get to this case, then we know that both aren't null. So if this second case runs, we know that one of them is null. If one of them is null, it means the other one is not null, so we have to return false. That would be where we would stop there. No point going further because they're not symmetrical. Then we can recurse here, so we're going to make sure, right, that if we're going to check symmetry between the trees, for example, we're passing in the root, right? Root is 1. We're passing in the left and right subtrees 2 and 2. Right? There's no point checking these sub-children unless the values in the nodes match first. So we want to make sure that left.val equals right.val. Well, if both of those are true, then we're going to want to check the left and right subtrees again, but with the proper parameters. So we'll call helper again, except we want to make sure that we're calling it for at least twice, because each call takes 2 subtrees and we have 4 children to process here. So if we want to check if they're symmetrical, right, if they're a mirror on top of each other, we don't want to match the left node's child. We don't want to match them perfectly. So if we called helper with 2, 3, and 2, 4, if we were to fold this in half like a sandwich, they actually would mirror. What we want to check is the farther out version. So we want to check 2.left and left.left and right.right. So we'll check left.left, right.right. That's going to check if those subtrees are symmetrical. But then we want to call it one more time, and we're going to check left.right, right, and right.left. Left dot right, right dot left. So this should be good. And so if we keep recursing, it should keep going. Let's just say we called it for, which we do call it for 1, right? We do root dot left, root dot right, so we're here and here. We check if they're both null, they're both not null, right? So we keep going. Well, is one of them null? None of them is null, so it does left dot val equal right dot val. Well, it does, so let's check the subtrees of those two nodes, where we're going to call helper with left dot left, which is this node, and right dot right, which is this node. Well, we have 3 and 3 now. So are both of them null? They're not. Is one of them null? Nope. So are the values the same? They are, and then we'll recurse for these nodes as well, the left dot left and the right dot right. They're both null, so we return true. Or go back up one recursive call, and then we check the left dot right and the right dot left dot right and the right dot left, and they're both null, so we also return true there. And so we would keep recursing and always making sure that the nodes in the subtrees are symmetrical. Okay, interesting. Oh, wait, left. I think it should be if left is equal to null or right is equal to null, then we would return null. There we go. So we'd be good there. Traverse the entire input tree once. Total runtime is O of n, where n is a total number of nodes. N is a total number of nodes in the tree, space complexity. We do visit every single node. That makes sense. That would be linear time. Number of recursive calls is bound by the height of the tree. That is true. In the worst case, the tree is linear and the height is O of n. Therefore, this. I see, yeah. The number of calls we do does almost is bound by the height of the tree. Therefore, space complexity, the recursive calls on stack is linear time in the worst case. Makes sense. So binary tree in order per traversal. We have a temporary tree. We have a data structure defined for the tree node, val left right with the constructor. Right. If any of the values are undefined, they automatically get 0 or null. Oops. So we have in order traversal. We have the root tree node. And they want us to produce an array of numbers. Given the root of a binary tree, return the in-order traversal of its nodes. Root of a binary tree, return the in-order traversal of its nodes. So So if they give us an input, binary tree input, we have 1, left null, right is 2, and the right of 2, okay? And we'll also notice that if this was a BST, the output would actually be the result. The output would actually be sorted in ascending order. Recursive solution is true. Could you do it iteratively? So inorder traversal, given the root of a binary tree. So inorder traversal is just depth first search, and inorder refers to the relative order between the left, root, and right node. So we could call a helper function. At the same time, they want us to return this nums array. We can call helper with root and then pass in nums. I'm not really certain about this one. And then we could pass in have a node, could be tree node or null, and we have this array which we're carrying around by reference. And actually, we wouldn't have to return anything. It's a binary tree. So we're not going to return anything. And actually, we'll just call helper and return nums. So what is the goal? They just want us to return the inorder traversal of its nodes, and that's just L and R. So we could L and R. So I guess you could just do nums dot push node dot val, and then we could do nums call helper again, and we'll check if node isn't, if the node isn't empty, right, then we want to push it onto the array. We want to call helper with the node dot left, passing in the number array reference. So I think this should work. So let's run it. If const nums equals an array helper root nums, we're starting at 1. If the node isn't null, 1 is not null, so we're going to push 1 onto the array. Now if we have helper, we're going to do helper of node.left. So now we're in node.left. Well, node.left is null, so we don't do anything. Right? We go back up here. Well, now we go with helper node.right. We're on node.right now. Well, since we're on node.right, it's 2. Well, 2 does exist, so we're going to push 2 onto the array. We're also within 2 now, so we're going to do node.left of 2. It's going to be 3. So the 3 node does exist. We're going to push 3 onto the array. So this actually wouldn't be NLR. This would be NLR. I mean L and R, which would be in order. So if we call 1, we call it with index 1, helper node.left. Well, what's the node.left of 1? It's null, we don't do anything. Then we push 1 onto the stack and we call helper node.right. Well, okay, now we're in helper node.right, which is 2. We're going to do helper node.left. Well, helper node.left is 3. Okay, now we're going to do helper node.left of 3. That's going to be null. We're not going to print anything. Then we're going to do nums.push 3, do helper.node helper node right of 3, it's going to give us null. We're going to go back to 2 and do node.push nums.push node.val, which is going to be 2. Makes sense. Let's do fried. Okay. So last time I did this problem was June 9th. The time complexity of this is linear time, I think. So we don't have to visit. Yeah, we do have to visit every node. But the space complexity would be linear time, because I think the number of calls is bounded by the height of the tree for this one as well, but in the worst case, the tree is linear. So we would take up linear space. So I'll try the follow-up. Recursive solution is trivial. Could you do it iteratively? Could you do it iteratively? So root tree node. Iteratively. Could you do it iteratively? Could we simply perform L and R in a for loop, keeping track of the nodes in a queue? Process, have a queue, which is just going to be an array that we only operate push elements at the front element. I'll work on elements at the back. We'll put root in first, and we'll say while queue.length is not equals 0. And we'll still keep nums, set it to an empty array. While the queue isn't empty, then I guess we'll take a node, because we'll do queue.pop. Once we have the node, which is going to be the root node, we want to process the nodes in the order of the queue. So can we replicate LNR iteratively? We're at the root node now, so we'd want to process the left node. Well, the left node, so say if node.left if node.left if node.left, what do we want to do with that? We have the left, we're at the left node of the root node. The left node of the root node, and it's null. What do we do with that? Well, if it exists, then maybe we push it, we add it to the front of the queue, maybe by doing node.left. And then maybe we would, well, we know that the node exists. We could do queue.unshift node if node.right. Maybe we could queue.unshift node.right. Okay, so we'd add null to the left side of the list. We'd add null, then we'd add 1 back. Well, we don't want to add 1 back because we just processed it. We don't want to add 1 back since we just processed this node, so it doesn't make sense to add back. Maybe you could process it iteratively with a stack. Wouldn't you still have to do a depth first search first? I guess it depends on if you can implement a depth first search iteratively. I don't know how to do that. Yeah, I knew you could do it with a stack. So you have the list of integers, which is an array. Then you have a stack. Then you have tree node cur, which equals root. So while cur does not equal null, and the stack is not empty, so I had while the stack isn't empty. So I should have had a variable cur, which would be equal to root. I should say, well, cur does not equal null. I was going to wrap the whole thing in an if, but this is also it makes sense though because you want to keep using reason cur probably. While cur does not equal null, stack dot push cur. Oh, with an inner loop. I see. I did node dot left, but we want to do another inner loop while cur does not equal null. Then we'll just push it. I'll just continue to use the queue. Okay, can you still use the queue? I think you just want to be last in, first out. We'll just keep using the array anyway. Q dot push cur, and then cur equals cur dot left. And then when you can't go left anymore, what would you do? Now looking at this loop, if you can't go left anymore, then you would pop something off the stack. Then you would cur equals stack dot pop. So you would do cur equal q dot pop. Take an element off the stack. I had node dot left here, but you can't use different branches. It doesn't make sense. So here they're pushing cur dot val. Why cur dot val? Cur dot val. Cur equals right. And then cur equals cur dot right. And then return nums. So it still is L and R. L and R still. So the 2 while loops. You slowly step through this. So while cur does not equal null, cur equals root, cur is not null, and q is not empty. So while cur does not equal null, we're gonna push cur, so 1. One is going in to the stack and then cur equals cur.left, so now cur equals 2. Well, cur isn't null. Right, cur equals 1. And then cur equals cur.left. Well, 2 isn't null, so we push 2 onto the stack. And cur equals cur.left, which is now 4. But 4 isn't null, so we push onto the stack node 4. Cur equals cur.left, which is now null. Well, now cur does equal null. So what do? We pop the node 4 off the stack. Now we're equal to 4 again. So if we can't go further, then we open up the queue. Open up the stack. And then we're going to push the element that was just on the stack. Now we have the node that was just on top of the stack. We're going to pop the stack. Do nums.push cur.val. Val is going to be 4. And cur is going to be good cur.right, but that's null. So cur is null, but the queue isn't empty. Well, cur does not equal null. Well, cur is null. I see. And then cur equals q.pop. So we pop 2 off the stack. Or popping 2 off the stack. We're going to push it. Cur equals cur.right. So now our cur equals cur.right again. And cur isn't null. Cur.law. I'm gonna do cur equals q.pop because we're null now. Then we push the current row, which is 5. Cur equals cur.right, which is going to be null again, but the queue is empty. So we pop and we're at 1. Since we're at 1 again, we're at 1 again. Cur does not equal null. Cur does not equal null. So why don't we push? Yeah, they lost me here. Why isn't 1? Why doesn't it just loop over itself again? Cur doesn't. 1 is cur. Oh, cur equals cur.right. So now we're back at 3, and then we go left till we can't go left anymore. In order with double while loops. Interesting. Yeah, that was interesting.